I really like this example, and you'll see why in just a second. Let's imagine that we've got two metal tracks, two metal railroad tracks, for example. So we've got these metal rails like this. We're going to assume that they're parallel and horizontal. So they're kind of extended down like this. And let's assume that they are 1.6 meters apart. So quite a bit more than this. So 1.6 meters apart, kind of like railroad tracks. Let's imagine that across these two tracks we have a metal bar. Could be more complicated than a metal bar, but that's the important idea. So across these two tracks we have a metal bar like this that makes electrical contact between the two tracks. The tracks have a voltage difference between them that causes a current to flow through the bar, let's say in that direction. So if these tracks were like this, the bar across like this has a current coming out of the board. So this electric current here, imagine, is kind of coming out towards us. There is also a magnetic field, let's say, pointing up between the tracks. So here are the tracks. Here are the tracks like this. The current is coming out of the board like this, and the magnetic field is pointing straight up this way. First of all, what force is there going to be? If there is a current, there's going to be a force on the rod. So what's the direction of the force? So I, B, I is out of the board this way, B is up. So the force on the rod, on the metal bar, will be to the left. There will be a force that tends to move the bar down the rail. This might be kind of like an idea for an electric train or something like that works with magnetic fields. Or kind of a first idea for something like that to develop it into. But let's imagine that the bar has a mass of 0.200 kilograms. And this is the part I like. There is a coefficient of static friction between the bar and the rod of 0.450. What I like about this is it's a throwback to some things that we learned from Physics 1111. So there is friction between the bar and the rails, and in order to move the bar, we have to overcome that friction. Remember, how much force do we need to apply to an object to start it moving? The force is Fs max. We have to overcome the maximum value of static friction, and Fs max was equal to mu s, the coefficient of static friction, times the normal force. Well, in this case, for a horizontal bar that's laying horizontally, all we have is the normal force from the rails, and that's going to be equal to the weight of the bar. So this is going to be mu s mg. My question is then, how much current do we have to have in the bar if the magnetic field is 0.50 Tesla, 500 Tesla, let's make that 3 sig figs. How much current do we have to have in the bar so that we have enough magnetic force acting on it to start the bar sliding down the rails? Well, what's the magnetic force? We know the force on a wire, on a current, is the force is equal to ILB sine theta. I'll just leave these as variables for the moment, but I, we know, will be whatever that current is. L, that's going to be the 1.60 meters. B, the magnetic field, 0.0500 Tesla. Theta, what's theta? Theta is the angle between I and B. What's that? I is out of the board, B is up. What's theta? 90 degrees. So sine of 90, what is sine of 90? 1. So we'll just take that right out of there, and we'll just say that the force, in this case, is ILB. That's the force that needs to overcome the force of static friction, which is mu s mg. In other words, this must be equal to mu s mg. Actually, to be honest, this would be the maximum amount of current that would not move the rail. What we would need is a current actually that's greater than this to overcome the static frictional force, but then we could actually cut back a little bit on that force because the kinetic friction, remember, is always less than the maximum static frictional force. So once we get it started, we could always cut back that current a little bit and just have enough current to match the kinetic frictional force if we wanted it to move at a constant velocity. So what do we have? Well, the current will then be I is equal to, this would be the minimum amount, we need something bigger than this, will be mu s mg divided by lb. And putting our numbers in, what do we have? 0.450 for mu s. The mass is 0.200 kilograms times g, 9.80 meters per second squared, divided by L, the length of the bar, 1.60 meters, times B, the magnetic field, 0.0500 Tesla. Multiply all that out, and what do we get? We get 11 amps. So we would need a current just larger than 11 amps to get this thing started, but then we could decrease it depending on what the coefficient of kinetic friction is. We could decrease the current to keep it moving. Very, very good. I would like to take a look now at a somewhat more involved problem. We're going to look at something a little bit more involved than just a straight current. Currents typically do not just come out of nowhere and disappear and end up with just a nice straight piece of current like this. They often form closed loops in circuits. Let's look at the current in a closed loop in a magnetic field and see what happens in that case. Here is our loops. You can imagine this is very much like this loop right here. So we've got a loop of wire, and then it comes up here, goes around this way, back down here, and we will assume then that, somewhere way out of the picture, we have it connected to a power source so that the power source is sending up current this way. We've got some current coming up that then comes over this way, up this way, over here, down here, over here, back down here, and then back down to our power supply somewhere way down below. Let's imagine that all of this is residing in a magnetic field. This whole thing is in a magnetic field that is pointing to the right. So there's a magnetic field all through here pointing to the right. I'm just not going to draw it over here because I want to draw some other things here. What I would like to do is figure out what are the forces acting on each of these parts of the loop. I will call this part, this section down here, part 1. This is part 2, part 3, part 4, part 5, part 6, part 7. What's the force acting on each part? To be specific, let's put some distances in here. I'm going to say that this length of the loop, we'll call that length A, while this length, we'll call that length B. So we're assuming we have a rectangular loop, A by B, that is in this magnetic field that way with a current I, and it's the same current through each section. So let's look at the forces on each part. First of all, on part 1, F1. What's the force on F1? Well, I'm not worried about how long it is. Let's think about what's the direction. Well, we've got a current up, magnetic field to the right, so the force is into the page. I'll just say this is into the page, while what about the force on section 7? Assuming it's the same length as section 1, we've got the current down, the force to the magnetic field to the right, the force is out of the page. So, out of the page. Whatever those forces are, the main point I want to think about is that they are going to cancel out. If we have these two wires and the wires here, they're actually wrapped around each other. You can imagine that if you want. The two wires are so close together and the forces are in opposite direction, they cancel each other out. So whatever happens on section 1 and section 7, the net force will be 0. We'll ignore that now from now on. Let's look at section 2 and 6. They are in the same direction to the right. Well, I'll kind of group them together. What's the force on section 2, 6? Force on section 2, 6. What's the direction of the force? The current is to the right. The magnetic field is to the right. What's the direction? What's the force? It's 0. We know the angle between I and B is 0. I, B, the angle between them is 0. The force is 0. So we have no force on section 2 and 6. What about section 4? Section 4. What's the force on section 4? What's the angle between I and B? It's 180 degrees. Sine of 180 is 0. Again, the force on section 4 is 0. What about section 3? The force on section 3. What is that? Well, the magnitude of the force will be ILB sine theta. I is the current. L, what's L? What's the length? Well, in this case, it's B, little b. ILB, B, big B, the magnetic field. Sine theta. What's theta in this case? I is this way, B is this way. What's theta? 90 degrees. Sine of 90 is 1. That's it. The magnitude of the force on section 3 is I, little b, big B. What's the direction? Current is up. B is to the right. Force is into the page. So the force on section 3 is into the page. There is F3. What about F5? F5. The magnitude is ILB, again, I, the current. L, again, little b. B, meaning B, the magnetic field, big B. Sine theta, again, theta is. I is down. B is to the right. What's the angle between them? 90 degrees. Sine of 90 is 1. So the magnitude of the force, F5, is I, little b, big B. What's the direction? I is down. Magnetic field to the right. Force is out of the board. There we go. What do we notice? F3 and F5 would also cancel each other out. But let's think about this for a second. Would they have no effect on the loop in this case? F1 and F7, they were on two wires that were right next to each other, maybe even wrapped around each other. They cancel each other out and have basically no effect on the wire. What about F3 and F5? Well, F5 is going to push this wire out and this wire in. This wire out, this wire in. F3 in. There we go. This way in, this way out. Well, if I do that, if I push this one out and this one in, what happens? The wire rotates. There is zero net force, but there is a net what? A net, can you think of what it is? From last semester, I'll give you a hint. A net torque. There is a net torque on the loop that will tend to rotate the loop. These forces will tend to make the loop rotate. I was going to say make the loop rotate. Make the loop rotate. That's a very, very interesting result. The net force, because of the current in this loop, in the magnetic field, the net result is a torque that tends to rotate the loop. In this case, I had arranged the loop so it was actually kind of in line with the magnetic field. What I'd like to do is actually rotate it slightly to make it a little more arbitrary, a little more general. And then we're going to rotate the loop and then we're going to look at it from above. So actually something like that. We're going to look at the loop from above. We're going to rotate it some small angle. We'll call it phi. And then we're going to imagine we're looking from above. So we're going to rotate our picture this way. So looking at it from above once we rotated it. I'm going to redraw the diagram with that rotated perspective, and we'll take a look at it. Here we are. Let's remember what we're doing. We have this loop that looks like this, and I'm going to talk about a particular direction. There's a direction that is perpendicular to our loop. So if this is our loop this way, I'm going to talk about a direction perpendicular to the loop, and I'll indicate it with this little part of the wire here. This is called the normal line. It is normal or perpendicular to the surface of our loop this way. Typically, normal lines to loops have a particular direction. We could choose this one or this one. We will use the right-hand rule to define a particular direction that corresponds to the direction of the current. Let's imagine, and this is the direction we already used, that the current is going up this side and then down this side. If you take your hands, we're going to use the right-hand rule, another method, and rotate your fingers in the direction of the current, so up this way, around this way, rotate your fingers in the direction of the current, your thumb, your right thumb, points in the correct or appropriate direction for the normal line. So not this one in, this one this way. If we had a current going the other way, then we would define the normal line this way. But for the current that we have, we'll define our normal line this way.